very much for inviting me. I'm now in my fourth day of my first visit to Korea and having a quite good, although a little bit busy schedule. I'm pleased to be here. So this talk is meant to be fairly friendly and introductory, and it involves a particular approach to the Riemann hypothesis, which goes back, well, actually it goes back to Riemann, but then more particularly to Polya in the 1920s, as we'll discuss. A lot of the discussion will be somewhat historical. So what the kind of object, the analysis object we'll be studying will be Laplace transforms of functions on the real line. For the moment, forget about this term here. Just set this real parameter lambda to be 0. We'll come back to that in a moment. In that case, this is the two-sided Laplace transform of a function f. The functions we'll be dealing with will be non-negative functions which are integrable over the whole real line. That means that except for a multiplicative constant, you could regard f as the density of a probability measure on the real line. And that's a natural thing to do for a probabilist. There's a very particular choice of f, which we'll talk about in the next slide or two, that comes up in the Riemann hypothesis, but we'll also be talking about a more general situation. So if this f is, if all you know about the f is that it's integrable, then if you want to do the two-sided Laplace transform, it's possible that that may not be well defined for a general choice of lambda, but it would always be defined for taking lambda to be negative, because then e to the lambda u squared f of u will go to 0 sufficiently rapidly that you can integrate with this exponential factor, and you will not only get a well-defined function for real w, but it will be also well-defined and analytic for complex w, and that's how we want to think of it. So for any value of lambda for which this makes sense for complex w, that's the situation we want to deal with, and for many f's, including the one that comes up in the Riemann hypothesis, it will be well-defined for lambda, not just negative, but positive lambda as well. And this is a notation. It's L for Laplace transform, the original function f, and then there's this kind of perturbing Gaussian factor there. And sometimes we'll want to regard f of u times the u, or a constant times that, as a measure, and we also will turn out that we'll be interested primarily in functions f or measures rho, which are even functions on the real line, that is invariant under changing u to minus u. Okay, and if you have any questions, please raise your hand or shout out. Okay, so as I said, we're interested in a very specific choice for the function f, which we'll call phi, and for that function, when that extra term isn't there, when that little lambda is 0, the Riemann hypothesis turns out to be, and this was known by Riemann, is equivalent to the statement that this, in that case, this Laplace transform will be an analytic entire function of complex w, and the Riemann hypothesis is equivalent to the statement that the zeros in the complex plane of that entire function are all on the imaginary axis. We'll use this because we'll be talking about the Laplace transform having this property of all the zeros being pure imaginary. I'll use a kind of abbreviation PIZ for pure imaginary zeros in that situation. The reason why, or the choice of the specific function is the one that makes this Laplace transform related to the Riemann zeta function in a particular way. Here's the zeta function, the infinite series of n to the minus s. To begin with, as you learn in calculus, that's a well-defined quantity for s real and bigger than 1. But it's easy to see that it also is perfectly well-defined if s is complex with real part bigger than 1. That function of s has a pole at s equals 1, but it also has an analytic continuation to complex values of s, except for that single pole. And the Riemann hypothesis has to do with the so-called non-trivial zeros in the complex plane of that function being on the critical line, which is real part of s equals 1/2. But we're going to, we, or actually Riemann, changed variables a little bit and it's translated by a 1/2. So in the new variable w, what the critical line at real part of s equals 1/2 is just the pure imaginary axis for the variable w. And then you take the zeta function, besides that small change of variables, and Riemann considered a related function by multiplying by these various factors. That's a gamma function, the generalization of factorial of s over 2. Multiplying by this gamma function has several consequences. The pole at s equals 1 is canceled by a 0 of the gamma function at s over 2 equals 1/2. The zeta function also has so-called trivial zeros along the negative real line at negative even integers, but those are canceled by the other poles of the gamma function. The gamma function introduces a new pole. It helped that the pole, well, let's see this. Well, anyway, by the time you multiply by the right factors, you've gotten rid of all the poles and trivial zeros, and so this function now, its only zeros are in the critical line, in the critical strip, and so you don't have to worry about the trivial zeros. This extra pi to the minus s over 2 has another symmetrizing property, which is not particularly obvious, but also known by Riemann, and expressed in terms of this function phi. So this is the explicit formula for the function phi, whose Laplace transform we want to look at, both for little lambda equals 0 and then for general lambda. It's this infinite series. So let me make some elementary and less elementary comments about this function. First of all, it's well defined for real u, in that we only consider it for real u, because for any real u, this is a pi e to the 4u is a real number, positive number, and so e to the minus n squared times that is going to 0 very rapidly. So despite these other factors, this is nicely convergent, and it converges for all real u. So it's well defined for all real u. There's another feature of it, which is not obvious at all, but was already known by Riemann. It's that this function of u is actually an even function. It does not look even, but it can be shown to be even in various ways. And we will just take that as given, or derived by Riemann. Another feature is that this goes to 0 very rapidly as u goes to plus infinity. That's basically because it behaves pretty much like this factor. It goes to 0 like e to minus an exponential. The factor when n equals 1 is e to the minus pi e to the 4u, which goes to 0 super exponentially fast. Now, it's not clear from the formula how it behaves for large negative U. However, we have already decided, as Riemann told us, that it's an even function, so however fast it decreases for large positive U, it also does the same thing for large negative U. So this is a very rapidly decreasing function, and certainly the Laplace transform is well defined, and it will be well defined even with the lambda there, because that e to the lambda u squared is overridden by this very exponential of an exponential decay rate. Okay, another feature is that this function, as we said before, we were interested in functions f that were positive on the real line. So let me give you the proof that this function is positive. When u is greater than or equal to 0, you can easily check that each one of these factors is positive, non-negative, positive, I guess, because, well, e to the 9u is bigger than e to the 5u, and to the fourth pi squared is bigger than 3/2 n squared pi, and so it's term by term positive or non-negative. It's no longer term by term positive when u is negative, but you don't have to check there because we already were told by Riemann that it's an even function, so it also will be positive for function for negative u. So let me show you what the graph looks like, which at least numerically verifies the various statements I just made. So there's the graph of the function. This is 0 here, and the fact that it goes to 0 like e to minus some constant e to the 4u, it shows up here that it's essentially 0 already for u, past 0.3 or less than minus 0.3, because it's e to minus such a big number that you can't even see that it's not 0. It also clearly, according to this little numerical calculation, does look even, as Riemann told us, and it's also non-negative because it's always above. Here's the u-axis, and it is non-negative. So it looks like nothing very interesting. I mean, very unusual. It looks something like a normal density function, except that it goes to 0 much more rapidly than e to the minus u squared. That's why it's practically 0 already over here. And the Riemann hypothesis, this unremarkable looking function, is equivalent to the statement that the two-sided Laplace transform of this function as an analytic function for complex W, all of its zeros are pure imaginary. But it's a little bit misleading because even though this graph doesn't look very unusual, you can't just replace it by something that looks similar and prove that property of the Laplace transform. That might be a useful result, but it would not tell you anything about the Riemann hypothesis. It has to be exactly this particular function. Okay, so now some of the history. Polya, I believe, was the first to put in that perturbation e to the lambda u squared. The formula with lambda equals 0 was already known by Riemann, and Polya said, well, let's perturb that formula by putting in e to the lambda u squared, and maybe besides having pure imaginary zeros for lambda equals 0, which is what you want for the Riemann hypothesis, perhaps you have that pure imaginary zeros property for any value of lambda. In the process of thinking about such things, Polya proved some important features. Namely, there's a kind of monotonicity property in the behavior of the zeros. Once you have this pure imaginary zeros property for some particular real value of lambda, say lambda 1, then making lambda any bigger than that preserves that property. It sort of helps it, or at least doesn't hurt it. once the zeros are pure imaginary, they stay pure imaginary. When you increase lambda, whether the lambda 1 is positive or negative, that's the case. On the other hand, if you decrease it, well, that might hurt it, whereas increasing it doesn't hurt and could help. And he hoped, or maybe even thought, that the pure imaginary zeros property would be true even when you hurt it, that is, made lambda negative, even large and negative. Perhaps that would still be the case. We'll find out in a moment that that's not so. But in the other direction, De Bruijn, in a paper in the 1950, Dutch mathematician, showed, based on the fact that you already know that the zeros of the zeta function are in the critical strip, and it turns out that that's when lambda equals 0, they're in the critical strip, that's here. Making lambda positive not only doesn't hurt, but actually helps. And he gave a quantitative version of that statement by showing that because you begin with zeros in the strip of a certain width, if you make lambda big enough, related to the width of the strip, and big enough is 1/2 or bigger, then even if the zeros were not all pure imaginary to start with, they will be by the time lambda is 1/2 or bigger. So that was De Bruijn's result. If you help things by making lambda greater than or equal to 1/2, then you will have all pure imaginary zeros. So I in a 1976 paper, for reasons that I'll try to discuss a bit later, they were motivated by some questions in statistical physics or mathematical physics. I was interested in this kind of question, not really so much because of the Riemann hypothesis, but for other reasons that I'll mention. And the process studied basically what functions f, little f, have the property that Polya hoped would be the case for the Riemann function, capital phi. And in the process of studying that, I discovered that this property that Polya hoped for could not be true for the function phi. That is, there is some lambda, maybe very negative, but some finite lambda, so that even if you had the pure imaginary zeros property when lambda equals 0, which would be the Riemann hypothesis statement, eventually when you make lambda sufficiently negative, you don't have that property. So because of that fact and De Bruijn's result and this monotonicity property of Polya's, that tells you that there's a specific kind of critical value of the parameter little lambda, which we call capital lambda, which is the dividing line between having the pure imaginary zeros property or not. If you're below that value, then you don't have the pure imaginary zeros property. If you're at that value or above, you do. The capital lambda is finite. That follows from this result of mine, and it's less than or equal to 1/2. That follows from De Bruijn's result. And the fact that there's a well-defined critical value, that really was from Polya's kind of monotonicity result. So it's a dividing line between having the pure imaginary zeros property or not, and that's become called the Bruijn-Newman constant, since its existence was basically a consequence of these two results. The Riemann hypothesis is equivalent to the statement that constant is less than or equal to 0. Being equal to 0, that's the case you're originally interested in for the Riemann hypothesis. If lambda is less than 0, it would mean that not only is the Riemann hypothesis true, but even when you sort of try to hurt things a little bit by making lambda negative, it doesn't hurt the location of the zeros. They're still pure imaginary. That would be the case of lambda strictly negative. In that same paper, well, so this is repeating some of what I just said. The Bruijn basically gave this upper bound on lambda. I gave this lower bound. And I also made the conjecture. The Riemann hypothesis, as we just said, is the statement that lambda is less than or equal to 0. I made in that paper the sort of complementary conjecture that this constant is greater than or equal to 0. That means that, that basically the conjecture that it's not negative. If it were negative, it would mean if you perturb things even in the sort of bad direction by a little bit, you'd still have pure imaginary zeros. This says that even if the Riemann hypothesis is true, if you perturb it even a little bit in the wrong direction by this small negative lambda, then you no longer have the pure imaginary zeros property. So that can be described as saying if the Riemann hypothesis is true, it's only barely true because a small perturbation would stop, no longer have zeros pure imaginary. Okay, so there were these two bounds, upper bound and the lower bound, and the conjecture and the Riemann hypothesis, which is the lambda less than or equal to 0. And then people realized that one could greatly improve my lower bound of strictly bigger than minus infinity. And the first of those results was 1988, Chordos, Norfolk, and Varga. And then there were a series of improvements over a number of papers over a number of years. All of those papers had in common that the fact that they were based on looking at where the zeros of the actual zeta function are along the critical line. And when you find a pair that are quite close to each other, that's a pair which is sort of susceptible to being moved off the imaginary axis by small perturbations. Because in order to move off the real axis, basically a pair of zeros have to move to come together, become a double zero, and then they move off in opposite directions from the critical line, or in our case, the imaginary axis. And so people analyzed better places along the critical line far up where there were very close pairs of zeros, and those were used to get better lower bounds. First one minus 50, then after a series of improvements, there was a paper in 94 which gave a quite small lower bound, minus 4 times 10 to the minus 6th, and another sequence of papers, and finally that series of improvements, except for results of this year, which I'll mention in a moment, the best of those bounds was really quite small negative number, minus 1 times 10 to the minus 11th. So all these things are in the direction of sort of numerical evidence in favor of this lower bound, but they didn't prove the lower bound. There also was one important improvement of the upper bound, which is a paper of about 9 years ago by Key, Kim, and Lee, all three of whom I've met in the last few days, which is that lambda is not just less than or equal to 1/2, but strictly less than 1/2. Now, that doesn't look like such an impressive improvement, but as I'll mention later, actually some of the related results that they got and methods they used are actually quite important, including in some new work that's being done by other people. Yes.
How do you know that the critical point it must have the sort of pure imaginary zero property?
Yes, okay. So there is an answer to that question, which is the following. So let me just repeat the question. I think that's one back. Yes, so the question is, it's sort of obvious that that there's a dividing line between having the property and not. The only thing that's not obvious is what happens right at the dividing line. So how does one know that when lambda exactly equal to this capital lambda, you still have the pure imaginary zeros property? Well, the argument is the following. Consider the sequence of functions that you have as lambda approaches this little lambda approaches this dividing line from above. From above. So above, you have the pure imaginary zeros property. So now let lambda go through a sequence of values converging to capital lambda. For each one of those functions, the zeros are pure imaginary, but you now have a sequence of entire functions which is converging to an entire function. They're also bounded uniformly on compact subsets of the complex plane, and by general complex variable theorems, and the name of the theorem I can never remember, the zeros of the limiting function can only be limits of the zeros unless the limiting function is identically zero, which isn't the case here. So things cannot move off the real axis, the imaginary axis. So you know it's also true for the limiting case. So we had this long series of improvements, which were, as I said, sort of evidence in favor of this conjecture. The final word on the conjecture is that it actually has been proven, but only just this year. So that's in a paper by Brad Rogers and Terry Tao, which was posted in January of this year. They gave a proof of that conjecture. So it really is greater than or equal to zero. So indeed, any small perturbation in the bad direction, you no longer have the pure imaginary zeros property. The methods they use were kind of an extension of some of the methods used in the earlier papers, but instead of kind of focusing on sort of particular pairs of zeros that were close together to get specific bounds on this constant, they sort of looked at things more globally and sort of analyzed used known results about the spacings of the zeros along the critical line, and showed that if this conjecture were not valid, then by studying the way the zeros move as you vary the parameter little lambda, which is now called t here, this function is satisfying a kind of backwards heat equation in the parameter t, or little lambda, and that motion is such that it tends to make the spacings of the zeros more regular as t increases. And if you already had the zeros pure imaginary for some negative t, then you continue making t to move to zero, the spacings would have become regular enough that they would violate known facts about the empirical distribution of the spacings of the zeta function zeros. That's a very rough idea, which is all I could say about it, because I have not studied the details. There's some ideas that are used there that are kind of based on ideas from random matrix theory, although they don't actually use random matrix theory, but some of the same ways of thinking about things. In Terry Tao, in his polymath, one of his new polymath projects, where lots of people all over the world are invited to collaborate on mathematical projects, and a number of times it's resulted in actual definitive results and papers. So he started a project to improve the upper bound, which had already been improved from less than or equal to 1/2 to strictly less than 1/2 by He, Kim, and Lee, and using some of the related He, Kim, and Lee results. For example, that if lambda is even slightly positive, that's helping things, and it helps things enough. So even if you don't yet know for small positive lambda that all the zeros are pure imaginary, you can show that there are at most finitely many that are not on the imaginary axis. That can then be used with very hardcore numerical methods to get improved upper bounds. And if you can look at at the website, and the last time I looked, which was a few weeks ago, they had gotten the upper bound down from 1/2 to about 0.22, with the possibility of getting better bounds. But the experts in this subject, which I don't include myself, I'm a kind of, I'm not a somebody in analytic number theory. I sort of dabble in it, think from a mathematical physics point of view. The experts like Tao and Peter Sarnak, I don't believe that this kind of approach will actually lead to a proof of the Riemann hypothesis. Nevertheless, it's sort of nice to have one number that's telling you something about something sort of like how close to the Riemann hypothesis one is, sort of. Okay, so now I wanted to discuss a little bit about the mathematical physics background and relations to pure imaginary zeros properties, and also explain a little bit about why I was interested in the question which led to this 76 paper, and a little bit more about what the result of that paper was that I eventually applied to the Riemann hypothesis. So the mathematical physics background begins in a paper from 1952 about the Ising model, which I'm not even going to define. It's a certain statistical mechanics model, a collection of random variables and certain distribution. And for statistical physics reasons, Li and Yang, who are extremely famous theoretical physicists who won Nobel Prize in maybe 56, anyway, around then, not for this work, but for other work, motivated by questions in statistical physics, actually obtained a theorem which says certain functions generated in these Ising models have a pure imaginary zeros property. So one way of saying it is that you can generate certain probability measures rho, so that for little lambda equals 0 or or positive, you have the pure imaginary zeros property. Now that was back from the 50s. Then in the 70s, there was a subject that was developing called Euclidean field theory, which is these are sort of lattice versions of Euclidean field theories, are kind of like Ising models, but a little bit more general, in which part of the generality is that instead of studying the kind of discrete measures rho that came up in Ising models, you study measures with densities that are of the form e to minus some potential function, and then in some cases it had been shown that you could perturb by lambda for arbitrarily negative lambda and still have the PIZ property. Here's some examples that I'll talk about in a second. That kind of V, a function V here, or F, are particularly nice for Euclidean field theory purposes. And so I was interested in some other possible examples besides the ones that were already known. Just for the purposes of this talk, I'll call an F with this property. That was the property that Polya was hoping would be true for the function phi, but now we know it isn't. Anyway, I'll call such an F perfect. So an example that had been obtained by the people in Euclidean field theory, namely Steinman and Griffiths, was that the function V that was a fourth degree even polynomial like this did have this property. It turned out that that already was known by Polya in the 1920s, although the way it was done by Simon and Griffiths was a little bit more general, and the more generality was needed for the Ising model. But they didn't actually know, I'm sure, about Polya's results. But anyway, this example was already known by Polya and then was re-derived by Simon and Griffiths. So for Euclidean field theory reasons, I was interested in whether we could replace this fourth degree polynomial by hyperbolic cosine. Because if so, then one could study the hyperbolic cosine field theory and you'd have more tools to use. So that's what I was actually interested in, sort of hoping that that would be the case. And in the process of trying to decide that, I ended up figuring out what all perfect Fs were. And once I did that, and later on, if I don't run out of time, I'll show you what the formula is for those. It, of course, includes this class, but somewhat more general. But the class did not include the one I had been hoping for. Well, that was a sort of a disappointment from the mathematical physics point of view. On the other hand, it also did not include the capital phi of the Riemann hypothesis. Well, that meant that I had learned something about, related to the Riemann hypothesis, which then the paper that I wrote was sort of about that rather than about the failed result for Euclidean field theory. And the fact that the phi is not perfect, is not in this class of perfect Fs, that proves that this capital lambda is strictly greater than minus infinity, and that was what the previous part of the talk was about. So that's the kind of background. Okay, in the last few minutes of the talk, I want to talk about some other recent results that are a little bit related in spirit to the Rogers tau result, although not the methods at all, and they're not at all related to the Riemann hypothesis. But Rogers tau says that if you take the function capital phi and perturb it with any negative lambda, you no longer have the PIZ property. So here's another class of Fs, or measures rho, that also has that property, but it's quite different and not, as I say, not relevant for the Riemann hypothesis. If you have a measure rho, here's an example. It has a density that behaves for large absolute U like e to the minus u to the 3/2 power. That's something that decreases faster than exponentially, so its Laplace transform is perfectly well defined and analytic, nothing wrong with it. But it has the property that if you try to perturb in the other direction with a positive lambda, you won't have anything integral anymore, because e to the positive constant u squared will blow up compared to e to the minus u to the 3/2. So that's an example where for any lambda, no matter how small, you get a non-integrable function. Then our theorem number A, or letter A, is that in that case, you also have the same conclusion, although for different reasons, as Rogers and tau. Any small perturbation, you don't have the pure imaginary zeros property. Maybe you have it when little lambda is 0, but you don't have it for any strictly positive lambda. And we can give examples where you have it for lambda equals 0, but not for any strictly positive lambda. So that's a kind of interesting result, and we apply it to a different thing of some interest in probability theory and mathematical physics or statistical physics called Gaussian multiplicative cast, which I don't want to talk about except just mentioning it. But I do want to quickly mention that this theorem is a consequence of another theorem of sort of probabilistic interest, which I still find somewhat surprising, which I'll state and then pretty much end the talk after that. So here's, to state that other theorem, I need a definition. So we're interested in, this is stated in terms of random variables. It's really about their probability measures. So you could state this all in terms of a probability measure on the real line, and this statement, so this is just the name of the class of random variables or the class of probability measures on the real line. The random variable is equal to its negative in distribution. That means the measure is unchanged, is symmetric with respect to u going to minus u. It has to have a tail decrease at infinity fast enough so you can, unlike the theorem A, so you can multiply by e to a small positive, at least a small positive constant times u squared or x squared and still get something iterable. And third, it has this pure imaginary zeros property. That's the class of random variables, really a class of probability measures or distributions. And our theorem is the following. Suppose you have a sequence of distributions or random variables which converge in the weakest usual sense in probability theory. The Fourier transforms, not the Laplace transforms, but the Fourier transforms converge pointwise on the real line. That's this convergence and distribution. And each one of these variables is in this class. Then the limiting variable is in this class. Now let me explain why this theorem is, I find, surprising. The assumption that it's in the class, part of the assumption is that you have this sort of bound on the tail behavior of the distribution, that it goes to zero at least as fast as some Gaussian. But you don't make any uniformity assumption. The b that you can integrate against, the b x squared, e to the b x squared, or u squared, you can integrate against, might be very small as n gets large. No uniformity at all assumed. Nevertheless, the limiting distribution is in the class. That means it has some strictly positive b. That sounds too good to be true. Because one's used to the fact that in limits in distribution, if you want to have the limiting random variable or distribution have some nice property of its moments or moment generating functions or something, you should need to have a uniform assumption as you approach it. But you don't. So this sounds like it's wrong. The reason it's true is that somehow this mysterious pure imaginary zeros property forces uniformity without assuming it. So I'm practically running out of time. I'm not going to, the way this theorem, the theorem A is obtained from theorem B is actually fairly straightforward. And this is that entire proof, but I think I'll skip that and spend the last couple of minutes. 5:15. Oh, okay. Sorry. Okay, then I guess I'll talk about the proof. I'm sorry. I thought I started at 4. Okay. All right. Good. Okay. Then, so those of you who were happy that I wasn't going to talk about the proof, now I'll have to sit for a while. But you know, you can do other things. Okay. So let me go back to theorem. Thank you for pointing that out. Let me go back to this theorem. So this theorem says that if I have a measure which does not have Gaussian tails, so like something whose behavior at large absolute u is like e to the minus absolute u to the 3/2, for example, then if you multiply by any e to a small epsilon u squared, you get something non-integrable. Then it will not have, whether or not it has the PIZ property when little lambda is 0, it cannot have it for any negative lambda. That's theorem A. And now I want to explain why this convergence theorem implies theorem A. Okay. So suppose, proof by contradiction, suppose the conclusion of theorem A was not valid. That would mean that you had some choice of negative lambda, so when you perturb by that factor, you have something which does have the pure imaginary zeros property. Clearly, because the row is already even, this thing is also an even measure. And clearly, this thing does have this property because we've multiplied by e to a negative constant u squared, so we can put in a b there that's, let's say, half of lambda 0, and you get something finite. So this measure with the negative lambda 0 will have all three properties needed. Okay. Now remember that Polya said that once you have some value where you have the pure imaginary zeros property, if you go above it, that only improves things or doesn't hurt things. That would mean that every lambda above this negative value, you would have the pure imaginary zeros property, and you also automatically have the other two assumptions of the definition. So this should say rho sub lambda. So now replace lambda 0 by rho sub lambda. Then that rho sub lambda would be in this class for every lambda starting from lambda 0 and going upwards towards 0. But that sequence of measures, the rho sub lambdas, sort of obviously converges to the original rho because we're just getting rid of this factor. It converges in distribution. The Fourier transforms would converge pointwise. Now we have and I'll take a sequence of the lambdas going up to 0. Each one of them would be in this class. By theorem B, the limiting thing would be in the class. But theorem B, being in the class, says that you have this property for the limiting measure. The limiting measure is the original rho, but the original rho does not have this property. That was the assumption of theorem A, that if you put in an e to the b x squared, you get something non-integrable. So so there's something wrong. The something wrong was that the assumption that there was any lambda 0 where you had the property, and so that's the proof. So I find this theorem, I initially found that I'm getting used to it, sort of surprising, and this proof of theorem A is kind of peculiar because it uses this surprising result. Anyway, so that's an example of some recent work. The last thing I want to do is just say a word about both, or a couple of words about both the key ingredient in the proof of theorem B and a related thing which was behind which was in that old 76 paper when I characterized those perfect Fs, the ones which could be perturbed the way Polya wanted. So the key to the proof of theorem B is somehow to use this pure imaginary zeros property, and combining that with the Gaussian decay other assumption in the definition of the class Z, and using pretty standard infinite product Hadamard factorization formulas from theory of entire functions. That's the generalization to entire functions of factoring a polynomial over its roots. The roots here are pure imaginary by the evenness of the and realness of the random variable or its distribution. The pure imaginary zeros have to come in pairs. The pairs would be plus or minus I y sub k, where y sub k are real numbers running off to infinity. The y sub k's, because of the assumption about the assumption that you can e to the bx squared is integrable for some positive b, it follows that the zeros can't have to go to infinity fast enough to make the sum of 1 over y squared convergent. That's over here. The yks are real because plus or minus iyk are the zeros. The Hadamard factorization, you involve products of 1 minus z over its zeros. You combine the two zeros plus iyk and minus iyk together, and those two factors give you this. And then by the evenness, you can't have like e to a times z, and you can't have any higher order things in the exponent because, again, of the the Gaussian tail condition. So you're left with this kind of representation of this Laplace transform or moment generating function. And in particular, because moment generating function generates moments, the second moment of this random variable is up to a factor of 2 or 1/2 is the second Taylor coefficient in z at 0 of this function, and that turns out to be basically, well, this. So that's a formula for the second moment. And the kind of key in the proof of theorem B is that if you had a little bit of uniformity, if you knew that the second moments were uniform in, if you had a sequence of rows converging to something, and you knew that their second moments were uniformly bounded, then because of this relation, and this factorization, you could then show why the limiting thing is, you get enough uniform boundedness of the kind you need to get the result. And then there's a second argument which shows, again using this formula, that if the second moments weren't bounded, then you could not even have convergence of the Fourier transforms on the real line. You could not have weak convergence. So that's somehow the way that argument works. The Hadamard factorization also comes up in the old paper in the characterization of what functions are perfect, where you have this Polya property, and it turns out that basically it's things which are limits of things that look like, well, except here one's looking at the function itself rather than its Laplace transform, but after a few steps, the things you get are somehow limits of objects that have factorizations like this, and they don't have to be quite this simple. In particular, you can get the fourth power coming up, but you can't get too much besides that. So these are what all perfect Fs look like, and then it's not hard to show both that e to the minus hyperbolic cosine is not like this, and also the phi of the Riemann hypothesis is not like this, basically because this goes to 0 roughly like e to the minus u to the fourth, whereas the Riemann hypothesis, capital Phi, goes to 0 like e to the minus an exponential, so it can't be of this form. Okay, I think that's basically where I end. Thank you.